What happens is that if you look at the forces of the gravity here, of course, at this point here, the sun pulls on it, Jupiter pulls on it. Things are in a rotating frame, so there's an extra sort of fictional force that comes from the rotation. What happens is that all those forces balance out to zero at these points. And so if you were to stick something there, since the net forces acting on are zero, the thing ought to stay there, right? And so it would simply just follow Jupiter. I'm more interested in the mathematics. I mean, I'll leave it to the astronomers to look through the telescopes and see if they can find these things. I mean, I'm interested in the mathematics. Now, I should point out, I mean, Lagrange, 200 years ago or whatever, predicted the existence of these asteroids. Observations since Wolf in 1906 actually shown that these asteroids don't actually just stay there. I mean, there's more forces involved, and there's other planets in the solar system and things, so there's more forces. What happens, and this is going to be hard to draw since I've cut off the board on myself, but what happens is that these orbits, these Trojans actually move in a horseshoe-shaped orbit around the orbit of Jupiter. So they move back and forth along Jupiter's move around. So this Jupiter moves and the horseshoe moves with it, and these asteroids move in this horseshoe-shaped region. So that's actually quite fascinating. So, I mean, I did both my master's thesis and my PhD dissertation on this kind of stuff. Again, I was looking more at the mathematical there. I'm looking at, that's what interests me. Of course, it's great because I have a medium in which I can explain these ideas that people relate to. They understand planets and asteroids, so it's not abstract. So that's what's nice about this. I can actually explain it to people without getting too mathematical. So that's what's really nice about this stuff.